This is Psych 299 Statistics. I'm Dr. Larry Hatcher. We are up to part 35, the normal curve model and its variations. If you're a student in my class, you should have in front of you the document that looks like this, part 35, normal curve model and its variations. You can download this document and go to Canvas modules. And one of the Canvas modules that I published recently will be a PDF document titled P35, the normal curve model and its variations. You can open it in Adobe Acrobat Reader and you can add words to it in Adobe Acrobat Reader. It involves using the comments tool that's in Adobe Acrobat Reader. I've made available to you a document that shows you how to add words to a PDF. Look for the section in Canvas modules that includes the document, Learn How to Add Words to a PDF. They give you step-by-step instructions on what tool you need to open up in Adobe Acrobat Reader in order to add words to this PDF. Obviously, you're welcome to use whatever app you want in order to add words to it, but this is one way that works. Okay. Part 35, normal curve model and its variations. In this document, some important words have been blanked out. Dr. Hatcher will fill in the blanks in lecture. You remember from a previous presentation of mine, I indicated that some of these mini chapters are complete. You don't have to wait for me. You can go ahead and start studying them with my study guide in hand. Other of these mini chapters, like this one, is blanked out, meaning most words are there, but on some pages I have blanked out a few important terms. I will lecture and show you what those terms are. You need to fill in the blanks, and you'll use Adobe Acrobat Reader or whatever app you like in order to add those words. What's the outline for this mini chapter? I'll talk about what is the normal curve model. I'll discuss the issue of tails of distribution, which is going to play an important part in this course, especially later when we get to significance testing. And I will talk about skewed distributions, symmetrical distributions, and skewed distributions, something that we'll have to worry about all semester long. I'm on page 35-1, and let's fill in our first blank. A bit down on page 35-1, we have this section, the normal curve model. Normal curve model is the most common model of how nature operates, at least the kinds of variables that we as psychologists study. Normal curve model is based on the concept of the normal curve, what some textbooks refer to as the Gaussian distribution, what some refer to as the bell-shaped curve, because it is bell-shaped. The normal curve model is symmetrical, which means that the left side of the distribution is a mirror image of the right side. There, we have filled in our first blank. In most places where you see an asterisk in the margin, that's going to be a place where you will need to fill in a blank, and you'll also see a big blank line on that line. In most cases, I will have filled in the blanks using a red font so that it stands out so that you don't miss them. Normal curve model, most common model of how nature operates based on the normal curve, bell-shaped and symmetrical, meaning that the left side is a mirror image of the right side. For an example of normal curve, see the figure that I have on the next page. It's fictitious distribution of IQ scores. The top part of the figure shows frequency chart in which each dot represents a person. Bottom part of the figure shows the smooth version of the curve. What does he mean by that? Let's go to page 35-2. Let's make this thing smaller so we can see the top and the bottom at the same time. I'm on page 35-2, distribution of IQ scores. Imagine this. You have administered an IQ test to a large sample of individuals. For each person, you've computed their IQ score. This is one of those tests where the typical score is 100. It's possible to get higher scores than that, but it's unlikely to get scores much higher than 120, 140, and so forth. It's possible to get lower scores than that, but you're not likely to see people scores much lower than 60 or so. This is a frequency distribution. Notice the little F on the y-axis indicating that we're counting how many people had each score. The dots represent people. We have a lot of people that had a score of 100 on this IQ test. There's a dot, which means a person got that score. Here's a dot, means a person got a score. There's a lot of dots above 100, meaning a lot of people got those scores. As we move away from 100, fewer and fewer people show IQ scores that high. As we move away from 100 in the other direction, fewer and fewer people show IQ scores that are that low. Now, theoretically, most of the time that I show you a distribution in this class, theoretically, this is the kind of distribution that I'm showing you, where there's a very large number of little dots in the distribution. Each dot represents a person. It's unwieldy to have to draw distributions like this all semester long, where there's going to be dozens or hundreds or thousands of little dots in it. Wouldn't it be easier if I just drew a line that captured the top of the distribution and showed you the shape of the distribution? That is how we typically do it in a statistics course. This figure in the bottom half of the same page shows you the same distribution. Once again, we're looking at IQ scores. Once again, we're plotting frequencies. In this case, rather than drawing all the little dots, I've just drawn a line that shows the general shape of the distribution. The fact that a lot of people got scores around 100, and frequency drops off as you go much above 100. Frequency drops off as you go much below 100. So that's the kind of distribution that you'll see all semester long in my notes. We go to page 35-3, the concept of tails of distribution. Tails of distribution is that portion of the distribution that contains extreme scores that are low in frequency. In other words, scores that are uncommon, scores that are atypical. I have an illustration about this in the next figure. I believe I'm going to have to shrink it down again to be able to see this on the screen. I am on page 35-2. 35-2, we have a figure, once again, frequency distribution, norms, mostly normally shaped distribution, IQ scores. Most people have IQ scores around 100. The tails of the distribution is that part of the distribution that contains scores that are low in frequency, in other words, scores that are uncommon. Relatively small number of people are out in this lower tail of the distribution. Relatively small number of people are out in this upper end of the distribution with really high IQ scores. Now, that may seem real obvious right now. It may not seem like a big deal, but this business of scores out in the tails of the distribution being uncommon, infrequent, that's going to play a big role later in the semester when we start talking about significance testing, p-values, and such. We go back to normal size and page 35-5. 35-5, skew distributions. Skew distribution is a distribution that's similar in shape to the normal distribution, except if it's a skew distribution, that means it's not symmetrical. It has a pronounced tail. If it's a skew distribution, that means it's going to have a really long tail that points in the direction of the higher scores, or it's going to have a really long tail that points in the direction of the lower scores. And we have a different name depending on which side of the distribution has the long tail. First up, negatively skewed distribution. Negatively skewed distribution has a pronounced tail at the negative or lower end of the distribution, where the lower, more negative scores appear. Now, I'm taking some liberties here and saying more negative scores. Scores either negative or it's positive, but I think of the scores that are more extreme in the low direction as being more negative. At least that's a mnemonic device that makes it easier for me to remember what a negatively skewed distribution is about. It'll probably help you as well. If it's a negatively skewed distribution, most scores are bunched together at the upper end of the distribution. As the scores decrease, there's fewer and fewer people with those lower scores. For example, see the next figure. It's a distribution of grade point averages at a college where most of the students are gifted. What would a distribution of grade point averages look like at a college where most students are gifted? They have high levels of academic ability. For that sample of college students, you assess their grade point averages. Yeah, I believe I can get it all this way. You assess the grade point averages. You plotted the frequencies of the grade point averages. This is what you got. Distribution of grade point averages where most people are gifted. If they're gifted, if they have high levels of academic ability, most of them should have relatively high grade point averages, 3.5, 3.7, 4.0. Notice their scores are bunched together here where the higher scores are up here. But not everybody gets high grade point average. There's some people that get lower grade point averages. There's fewer and fewer of them, but they do get low, low, low. And the fact that there's relatively few of them means that this distribution is going to have kind of a long skinny tail that points in the direction of those lower grade point averages. Negatively skewed distribution. My tip, look for the, if I ask you a question about a skewed distribution, you should look at the shape of the distribution or even draw it on a piece of paper as you're taking the test. Look for the long tail. If the long tail points in the direction of the lower scores, if the long tail points in the direction where negative scores would be, it's a negatively skewed distribution. That's my memory device. Page 35-7, positively skewed distribution. Page 35-7, positively skewed distribution is one that has a pronounced tail at the positive or upper end of the distribution where the higher, more positive scores would appear. If it's positively skewed distribution, most scores are bunched together at the lower end of the distribution. As scores increase, there's fewer and fewer people with those higher scores. For example, the next page shows distribution of annual income among families in the U.S. Annual income usually forms a positively skewed distribution. Let's see an example of that and think about why it sort of makes sense that a distribution of income is going to be positively skewed. I am on page 35-8. I'm going to have to move my document so that you can see everything I want you to see. Page 35-8, distribution of annual income among families in the U.S. We have a long tail. Well, down at the bottom on the x-axis, we're plotting annual income. Low incomes here, these are the people that got $0 per year. Higher incomes up here, these are people that got $500,000 a year, but the tail would go on in this positive direction if we had enough space on the page to plot it out. It's a positively skewed distribution because we have a long tail that points out in the direction of the higher scores, what I think of as being the more positive scores. If the tail points in the direction of the higher, more positive scores, it's a positively skewed distribution. Most scores are bunched together at the lower scores. Small number of people with the higher scores, they form that long, skinny tail that goes out in the direction of the higher scores. Why does it make sense that annual income should be positively skewed? Well, no one can make less than $0 per year. It has a bottom end. So a lot of us would be bunched together here with low incomes of $30,000 a year, $50,000 a year, and such. But theoretically, there's no limit on how high your income could be. So out in this direction, we have people that majored in electrical engineering in college, people that majored in chemical engineering in college. We have physicians that are in specialties that are particularly valued. We have people that work on Wall Street and get big bonuses. They are way out here on the right side, and they give it a long, pronounced tail on the right side of the distribution, creating a positively skewed distribution. And that is the end. Let's make sure that you can see the very bottom of that page. Yes, the very bottom of that page said positive skew. That is the end of this module. This module was Part 35, Normal Curve Model and its Variations.